Okay, so this is our first video moving into chapter 12 of the matrices, and just an early apology if I sound a little stuffed up today. I'm not particularly well, but anyway, had a COVID test just in case, so we'll wait and see, but I'm sure it's just a cold. Anyway, so we want to have a talk today about the idea of an inverse matrix, and in subsequent videos we'll see why an inverse matrix is necessary. But essentially, when we're solving a matrix equation, so that is an equation that involves matrices, we've seen a couple of these before now, but they've been very, very simple ones which have avoided a particular problem that we have. And one of the issues we have when dealing with matrices is that there is no such thing as division for matrices. And so one way to get around that lack of division as a process when we're solving equations is to use the inverse matrix. Well, the only way to get around it. So today I just want to introduce what the inverse matrix is and how we're going to find the inverse matrix. And then in subsequent videos we'll look at solving matrix equations and applications of that. So yeah, we really just want to practice the technique here. Okay, so the first thing to recall is this idea of an identity matrix, and I did mention earlier that this is sort of, whilst it seems a little trivial, it becomes important later on, and it's important in its role in creating the inverse matrix. So the identity matrix is a square matrix where all the entries are 0 except for the leading diagonal of 1s. Okay, so for 2 by 2 matrices that would be this, for 3 by 3 matrices that would be this, and obviously we can extend beyond 3 by 3. And these matrices are important because they're kind of like the matrix equivalent of the number 1. If you multiply any matrix by an identity matrix, as long as the dimensions mean that that multiplication can happen, you'll get the original matrix. So A times an identity matrix is just going to give you A. Similarly, the identity matrix times A will also just give you A. This is one of the few instances where matrix multiplication is commutative. A times I is the same as I times A. Okay, and obviously for the orders to work in those multiplications in both directions, A would also need to be a square matrix. Okay, so let's just show that that's true for this particular matrix. So let's just do a 2 by 2. So if our matrix is 3, negative 2, 1, 7, we want to find A times I. And obviously, in order for the multiplication to work, that identity matrix would need to be a 2 by 2 matrix. So A, which is 3, negative 2, 1, 7, and we're multiplying that by a 2 by 2 identity matrix. So that is 1, 0, 0, 1. Okay, and again, let's think about how matrix multiplication happens. So we know row times column. So top row times left column will go in the top left, and we're going to do that by, then when we multiply the row by the column, we do 3 times 1, which is 3, plus negative 2 times 0, which is 0. So we're just going to get 3. Okay, and then top row times right column is going to give me the number in the top right. Okay, so 3 times 0, which is 0, plus negative 2 times 1, which is negative 2. So 0 plus negative 2 is negative 2. Bottom row times left column gives me the number that goes in the bottom left. 1 times 1 is 1, plus 7 times 0, which is 0. So we just get 1. And then finally, bottom row times right column goes in the bottom right. 1 times 0 is 0, plus 7 times 1 is 7. And so what we actually see is when we do A times I, it is just the same as A. Okay, let's check that if we do it the other way around, the same is also true. So if we put the identity first, so 1, 0, 0, 1, and we multiply that by matrix A, which is 3, negative 2, 1, 7. And again, let's think about how matrix multiplication works. So top row times left column goes in the top left. 1 times 3 plus 0 times 1, so that's just 3. Top row times right column goes in the top right. 1 times negative 2 plus 0 times 7, so that's negative 2. Bottom row times left column goes in the bottom left. 0 times 3 is 0, plus 1 times 1, which is just 1. And bottom row times right column, 0 times negative 2 is 0, plus 1 times 7 is 7. And so again, by multiplying the identity times A, we still get A. So A times the identity, same as identity times A, and both of those things just give A. So it's like the matrix equivalent of the number 1. 1 times any other number just gives that number. The identity matrix times any other matrix, as long as the multiplication can happen because of the orders, identity times any other matrix will just give that matrix. Okay, so inverse matrices. Sorry, there's a inverses matrices, so inverse matrices. So for any square matrix, let's call it A, there could be a matrix, another matrix called B, so that A times B is the same as B times A, and it gives the identity matrix. And if that can happen, that matrix B is said to be the inverse of A. And we don't usually call it B, we would call it A to the power of -1. Okay, so this would be inverse of A. Okay, obviously if your original matrix was B, it'd be B to the -1. Okay, so what we're seeing here is that if we have a matrix that when we multiply it by its inverse, if we have a matrix then when we multiply by another matrix we get the identity matrix, then those two matrices must be inverses. And again, we'll find that the matrix multiplication is commutative. We could do the matrix times its inverse or the inverse times the original matrix, and both would give us the the identity matrix. It's sort of the same as in number world saying that half times 2 is the same as 2 times a half, and they give us 1. Half and 2 can be thought of as inverse matrices. Oh, sorry, not matrices, can be thought of as inverses. They're not really inverses, they're reciprocals when we talk about numbers. But essentially, when we multiply them together, we get 1, and that's an important tool when we're trying to solve equations. And the same is true, the inverse matrix will be similarly useful. Okay, show that this pair of matrices are inverse matrices. So what we should see, if they're inverses, when we multiply them together, they should give the identity matrix. So let's see. Let's also check that it works both ways. So if we call that A and that B, if we do A times B, we get 1, -3, 2, -5, and we multiply that by -5, 3, -2, 1, and again, top row times left column, 1 times -5 is -5, plus -3 times -2 is +6, so -5 plus +6 gives us 1. Top row times right column, 1 times 3 is 3, plus -3 times 1, which is -3, so 3 plus -3 is 0. Bottom row times left column, 2 times -5 is -10, plus -5 times -2 is +10, so -5 plus +10 is 0. And bottom row times right column, 2 times 3 is 6, plus -5 times 1, which is -5, so 6 plus -5 is 1. And so we indeed see that A times B gives us the identity matrix, and we should be able to check that if we do it the other way around, we get the same. -5, 3, -2, 1, times 1 -3, 2 -5. Okay, so again, top row times left column, -5 times 1 is -5, plus 3 times 2, which is 6, so -5 plus 6 is 1. Top row times right column, -5 times -3 is +15, plus 3 times -5, which is -15, so +15 plus -15 is 0. Bottom row times left column, -2 times 1 is -2, plus 1 times 2 is 2, so -2 plus 2 is 0. And bottom row times right column, -2 times -3 is +6, plus 1 times -5 is -5, so +6 plus -5 is 1. And so we find that it equals the identity matrix. And so therefore, A and B are inverses, which means that B is the inverse of A. Or we could say A is the inverse of B. Okay. Okay, so finding the inverse of a 2 by 2 matrix. Now we could go through a lengthy process of proof here, but I'm just going to give you the rule. So if your original matrix is A, B, C, D, So if matrix A is A, B, C, D, then the inverse of A is this. Now that looks really ugly, there's a lot going on there, but if we notice that actually all of the numbers in here have a common denominator of AD minus BC, if we factor that out, so we put it out the front, we can actually get a sort of easier to use version of the inverse matrix. So if your original matrix is A, B, C, D, your inverse matrix is 1 over A times D minus B times C, and then inside the matrix we do some rearranging. So what we notice here is that A and D have swapped around, the numbers in the leading diagonal have swapped around, okay? And the numbers in the other diagonal have stayed in the same position, but they've become negative. They've been multiplied by -1. Okay, so that's the process that we want to be able to execute. So this particular denominator, AD minus BC, that's quite an important number, and that has its own name, and it's called the determinant. Okay, and we call that det A, determinant of matrix A, or det B, determinant of matrix B, and that would be just AD minus BC. So multiply together the numbers on the leading diagonal, subtract, and multiply together the numbers on the other diagonal to work out the determinant of the matrix. And so we can write our inverse as 1 divided by the determinant, which is AD minus BC, and then inside the matrix, switching the numbers in the leading diagonal, so switching A and D, leaving B and C, leaving the numbers in the other diagonal where they are, but multiplying them by -1. Okay, so let's go through some examples. So here we have a matrix A, which is 1, -2, -5, 2. It's also worth noting that you can only have an inverse of a square matrix. Okay, so we're only going to be dealing with square matrices here. By hand, we'll pretty much just be dealing with 2 by 2 matrices. Or we will only be dealing with 2 by 2 matrices. The process of finding a determinant and an inverse for a 3 by 3 matrix or bigger is actually quite complex. We'll have our CAS if we need to deal with those, and I'll talk about that a bit further down. Okay, so A is 1, -2, -5, 2. First of all, we want to find the determinant of A. Determinant, remembering, is AD minus BC, and in this case, A is 1, D is 2, minus B, which is -2, times C, which is -5. So we have 1 times 2, which is 2, minus -2 times -5, which is 10. So 2 minus 10 is -8. The inverse of A is 1 over the determinant, so 1 over 8. And then we rearrange the matrix by switching the numbers in the leading diagonal. So we're switching the 1 and the 2, so it becomes 2 and then 1. And then we leave the numbers in the other diagonal, but we multiply them both by -1. So they're going to become +5 and +2. And so that would be the inverse of A. You can also, if you want to, multiply that fraction in. So it would be 2/8, which simplifies to 1/4, 2/8, which again simplifies to 1/4, 5/8, 1/8. Oops. But it's perfectly fine to leave the fraction out the front and to write your inverse as 1/8 times 2251, and that would generally be my preference. The only time I would actually multiply the fraction in, if let's say for example you had half out the front and all of the numbers in here were even, and so when you multiplied it in you didn't get any fractions. Okay, that's the only reason I would definitely multiply it in. Otherwise I generally leave it with the fraction out the front. Okay, so now we want to show that if we multiply our inverse matrix times our original matrix, we get the identity matrix. So we just want to verify that this is in fact the inverse matrix. So our inverse matrix is 1/8. Now I definitely would not use this version. Okay, definitely wouldn't use the version with the fractions for the multiplication. It will get really ugly. I mean, obviously you can use your CAS to help you, but I would personally stick with the version with the whole numbers in the matrix and the fraction out the front. And 1, -2, -5, 2. Now, whilst matrix multiplication isn't commutative, so we can't just switch the order and expect the same result, although in this case, because it's an identity and it's original, we could. So normally we can't switch the order of matrices, but number multiplication, scalar multiplication can happen at any time. So in this case, we wouldn't do 1/8 times this matrix and make fractions and then try and do that matrix times the other matrix. We're instead going to multiply together the two matrices while they've just got whole numbers in them, and then we'll multiply in the 1/8 at the end. Okay, So again, let's work out a matrix multiplication. Top row times left column is 2 times 1, which is 2, plus 2 times negative 5, which is negative 10. So 2 plus negative 10 is negative 8. Okay. Top row times right column, 2 times negative 2 is negative 4, plus 2 times 2, which is positive 4. Negative 4 plus positive 4 is 0. Bottom row times left column, 5 times 1 is 5, plus 1 times negative 5 is negative 5, so 5 plus negative 5 is 0. And bottom row times right column, 5 times negative 2 is negative 10, plus 1 times 2, which is 2, so negative 10 plus 2 is negative 8. And, sorry, I just realised I made an error, well, just a very small error, I've just left something out. My determinant's actually negative 8, so my inverse is 1 over negative 8, or negative 1/8, so there should be a negative out the front here. Okay, so that's fine. Alright, and so then, sorry, we've still got our, and that's where I've only done the matrix multiplication, I haven't multiplied in, I haven't multiplied in the negative 1/8 yet. So now if we multiply everything by negative 1/8, negative 1/8 times negative 8 is positive 1, negative 1/8 times 0 is 0, negative 1/8 times 0 is 0, and negative 1/8 times negative 8, you've got negative 1 on 8 times 8. Okay, 1/8 times 8 is 1, and you've got a negative out the front. So they're both negative, so you get positive, and 1/8 times 8 is 1. So we get positive 1. And so indeed, the inverse times the original matrix does indeed give the identity matrix, hence confirming that it is in fact the inverse. So sorry, please make sure you've added that negative 1/8 back to your answer to part B. Definitely should be a negative, which means if I had expanded out the brackets, there should be negatives in all of these. Okay. Sorry, expanded out the scalar multiplication in part B. Okay, question 4. Calculate the inverse of each of the following. Okay, so let's work out our determinant for each of them. So the determinant in this case is AD, so 4 times 2 minus BC, so 1 times negative 7. So that's 6 minus 7. 6 plus 7 is 13. And so our inverse, let's call this A, and we'll call this one B, and we'll call this one C. So therefore this is the determinant of A, and therefore the inverse of A will be 1 on 13, 1 on our determinant. We swap the numbers on the leading diagonal, so it becomes 2 and 4. The numbers on the other diagonal stay where they are, but they're multiplied by negative 1. So the number that was positive becomes negative, the number that was negative becomes positive. Okay, B, so determinant of B, AD, so 1 times 2, minus BC, so negative 4 times negative 3. So that is 2 minus positive 12, so negative 4 times negative 3 is positive 12. 2 minus 12 is negative 10. So our inverse of B is 1 on negative 10, or negative 1/10. Swapping the numbers on the leading diagonal, so it becomes 2 and 1. Multiplying the other two numbers by negative 1, so they both become positive. And there is our inverse of B. Matrix C, so the determinant of C, 3 times 4 is 12, minus, sorry, I'll write that out, AD, so 3 times 4, minus BC, so 2 times 6, so that's 12 minus 12, which is 0. Okay, and this introduces a problem for us because our inverse matrix would be 1 divided by 0, okay? And this is not defined. It's not possible to divide by 0, okay? And so therefore, inverse of C is undefined. So if the determinant of a matrix is 0, that matrix does not have an inverse, okay? And we have a particular name for that. We call them singular matrices. So if the determinant of a matrix is equal to 0, then the inverse of that matrix does not exist. And if a matrix doesn't have an inverse, I'm looking at the second dot point here, that is when the determinant is 0, it's called a singular matrix. If a matrix does have an inverse, that is its determinant is something other than 0, it's called a regular matrix. So a matrix without an inverse is a singular matrix. In example 4, which matrices are regular and which are singular. So obviously the first two, the determinant was non-zero, the determinant was something other than 0, and therefore we could find the inverse. So those are regular matrices. In part C, the determinant was 0, and so that is a singular matrix. Okay, so A and B are regular matrices. That is, their determinants don't equal 0. Okay, C is a singular matrix because its determinant does equal 0. Okay, calculating your inverses and determinants using your CAS. So let's just use that previous example just to show you how you're going to do this. So let's maybe just look at that matrix at part A. So if we're going to calculate the determinant, menu, number 7 for matrices, sorry, 7 for matrices, and then number 3 is determinant, and then you simply put your matrix in here. So we have a 2 by 2 matrix here, and it was 4, -7, 1 and 2. Hopefully we find the determinant's 13. Oh, it's 15, so obviously I have made a mistake. Oh, sorry. My apologies, I told you I wasn't very well. Lucky we checked with this one. Sorry, let's go back here and correct this error. So 4 times 2 clearly isn't 6. 4 times 2 is 8. And 8 minus 7, 8 plus 7 is 15. And so therefore the inverse matrix would be 1 on 15. Okay, my apologies for that. Okay, lucky we checked. Alright, and so therefore, and if you want to find the inverse of matrix A, you would simply type in your matrix. Okay, so 4, -7, 1 and 2, and you simply raise it to a power of -1 to find the inverse. Okay, so the power button is over on the left, right on the edge above the e to the power of x and below the equals sign, and then power of -1. If I press enter here, I'll get my determinant, which you can see if you expanded this 1/15 into your matrix, you would get 2/15, 7/15, -1/15, and 4/15. And so our answer is correct. We've just factored the 1/15 out the front of the matrix. Okay, so that's how you can use your CAS to find determinants and inverses. So menu 7(3) for the determinant. Inverse, you simply raise the matrix to a power of -1. Okay, so as I said, we can only do this by hand if we've got 2 by 2 matrices, and if you've got a 2 by 2 matrix, it's generally quicker to do it by hand than it is to type it into your CAS. However, as soon as it's a 3 by 3 or larger square matrix, we must use the CAS. Okay. Right, so let's, for example, let's work out for matrix B. So to avoid having to type the matrix in twice, I'm actually just going to take a line of working where I just type out my matrix. So 3 by 3 matrix, I'm just going to put the numbers in. 3, -2, and ultimately this will save me time in the long run because then I can just keep copying this line down when I want to find the determinant or find the inverse. So 0, 1, and 1. Okay, I'm just going to press enter. So that's matrix B that I've entered there. So if I want the determinant, menu, 7 for matrices and 3 for determinant, I'm just going to scroll up and press enter to copy that answer down into my determinant bracket. And so therefore the determinant is equal to 18. And the inverse of B, so again I'm just going to scroll back up and press enter to copy that down onto my next entry line. I'm going to raise it to a power of -1 to get the inverse, and press enter. And so I get 1/9, 1/6, -1/9, -2/9, 1/6, 2/9, 2/9, -1/6, and 7/9. And what we would actually see here, it's perfectly fine, I would just leave my answer as it is, but it does still have the same connection to the fact that there should be 1 over the determinant out of the front. So if I multiply this matrix by 18, just so I can see what would happen if I factor out that 1 on 18, I'd get 2, 3, -2, -4, 3, 4, and 4 minus 3, 14. So these are the same thing. If you multiply everything by 1 on 18, you'll get all these fractions. But I just want to be clear about the fact that even though it's a 3 by 3 matrix, you actually still have the 1 over the determinant out the front, but the rearrangement of the numbers inside is much more complex, obviously, because we've got more numbers. And similarly, the calculation of the determinant's quite a lot more complex. So you won't need to do it by hand if you have a 3 by 3 or larger matrix. Okay, work today is from a worksheet at the back of your red booklet in Appendix B.